Hello, physics. I'm not here today. You are going to be doing translational and rotational equilibrium problems. You need to have done the torque notes first. So if you didn't do that, get those notes from somebody. Get somebody to explain that to you, or this isn't going to make much sense. You should definitely have done the torque notes before you do this. So make sure you get those notes from somebody and you understand it. So we're still not applying this to anything. We're just learning the basics of torques before we apply it to anything. Usually you want something to be in translational equilibrium and rotational equilibrium. Translational means that there is no net force on it. It's in equilibrium. The forces are balanced. And we know if there's no net force, there's not going to be acceleration. And we know that no net force means that they balance. So the forces that are up equal the forces that are down. The forces that are left equal the forces that are right. So oftentimes we want our objects just to have translational equilibrium. We want them to stay where they are. We don't want them to go anywhere. We also do not want them to tip over or start to rotate. So we want them to have rotational equilibrium. Having rotational equilibrium means that there's no net torque. So the object is not starting to rotate. It could be rotating at constant speed, but that won't usually be the case in anything we're going to do. And if there's no net torque, that means that the clockwise torques equal the counterclockwise torques. So remember, translational has to do with forces and rotational has to do with torques. Okay, we're going to look at the examples from torque notes. This is the ones we did already. We're going to take that a step farther and we're going to add the force that produces translational and rotational equilibrium. So right now our pivot point is just, there's nothing there. Now in real life situation this would be like some kind of hinge, or there'd be some kind of forces here from, if that's nailed down or whatever, it's spinning. But in our examples, we didn't have any forces here, so this wasn't physically possible. So this whole thing actually, you can tell, would have been accelerating down. If there weren't any forces up and these were the only forces on this bar, it would have been accelerating down. So if we want translational equilibrium, that means we need the forces to cancel out. You can tell I have 10, 10, and 6. I have 26 newtons down. So to make translational equilibrium, I would need 26 newtons up. That's how I like to write it. I like to write what you need, so it's really clear this is what I need to add. I'm not going to write that the net force is 26 down. I'm going to write that I need 26 up. So you can tell for rotation, right now there's a net torque of going clockwise. Well, to make rotational equilibrium, I need to cancel that out. I'm going to need a torque that is 42 Newton meters counterclockwise to cancel that one out. So that was the same magnitude, just the opposite direction. So now I know I need 26 newtons, and I know I need a torque of that. So now I need to actually draw the force on here. So I need to figure out where to put it. I'm just going to use the torque equation. I know I need a torque of 42 and a force of 26. So I can figure out distance. I can figure out where to put it. So I get a distance of 1.6 meters. Remember that distance means distance from the pivot point. So how do I know if I need 1.6 meters this way or 1.6 meters that way? Think about it. I need a force up and I need it to make a counterclockwise torque. If I put it here, that would make a clockwise torque. So you can tell I need to put it here, a force up here, so it would make counterclockwise. And I'm going to add that to my picture. 26 newtons right here. And that's all there is to this. It's pretty simple when all your forces are straight up or down. Now remember, we did start from yesterday's note, so all this was already done. If this wasn't already done, you'd have to find your net torque first. Let's try a more complicated example. So again, we're looking at the notes, the torque notes. We're going to look at example 3. Same question. I want to add the force that produces translational and rotational equilibrium. Now, yesterday when we did this, we knew that only the perpendicular part of the forces cause torque, so that's all I figured out. I just put that right in here. We did the perpendicular component, sine. We did the perpendicular component. It was the opposite, sine. We did the perpendicular component. So my hypotenuse was 20, and I did sine because I wanted the opposite side, the perpendicular part. But now that we're doing translational, we need up to equal down. We need left to equal right also. So I do want these other components now. When I was just doing torque, I didn't want them, but now I do need them. So I'm just going to go through first and figure out all those components. And I'm just going to write them really neat here. You do not need to write this out. I'm going to break that into components. Remember, that's sine and cosine. My opposite side is the y, my adjacent side is the x. I cross multiply. Pause the tape here and figure out these other components yourself. Sine and cosine for both of them, and neatly write the components. I hope you matched me. Okay, let's figure out what forces I need to make this balanced. Well, I'm going to look at my left and right first. Last time I didn't have to do this. You can tell I've got 15.3 to the left. Well, look here. I have 15.3 to the right, so that cancels out. I have 26.3 to the right, so I'm going to need another 26.3 to the left to cancel that out. But now I'm going to look at up and down also. I've got 12.9 up and 12.9 up, but only 9.58 down. So you can tell I need more down. Add these up, subtract what I already have, and then you can tell how much more I need. I need 16.2 newtons down. Pause the tape and ask someone if you don't understand where I got the 16.2. But I can only add one force, add the force. I can't add two forces. So I need to figure out what one force is 26.3 point left and 16.2 down. I need to find this red force. It's been a while, but you know how to do that. Pythagorean theorem to get the magnitude, and inverse tangent to get the direction. So that's the force I need to add, 30.9 newtons at 32 degrees. This force would be enough to give me translational equilibrium. Let's look at the rotational. Remember, I did half of this problem already, so I know there's a net torque of 3.33 newton meters counterclockwise, so I need a torque of 3.33 clockwise to cancel that out. So I know I need to add this force in the right place to give me this torque. So now I'm looking at my torque equation to figure out where to put that force. Torque is force times distance to the pivot point. I know the torque I need is 3.33. But remember, in the torque equation, this is only the perpendicular force. So I'm not going to use this. I'm just going to use the perpendicular part. That's the only part that causes torque. So I'm just going to put the 16.2 in here. And I got a distance of 0.21. So remember, that means 0.21 meters from the pivot point. So is it 0.21 meters here or 0.21 meters there? Remember, I'm adding this force, and in particular this part is going to cause the torque. So basically I have it down, and I need to make it go clockwise. If I put down here, that would go counterclockwise. So I must put the down part here if I want to go clockwise. But remember, I need this to give me translational equilibrium. So I'm actually going to draw that on my picture. Right here, I need 30.9 newtons at an angle of 32. That is my answer. Now, when we actually do problems, that are representing real things, they won't be this complicated. But if you can do this, you can do the simpler problems.